Okay, let's continue our discussion. We're now on Meyerhoff's bearing capacity, shape, depth, and inclination factors. So we have here a table presenting the different bearing capacity introduced by Meyerhoff. You have the bearing capacity, you have the shape factor, you have the depth factor, and inclination factors. So we have also here some comments on the bearing capacity factor and sub gamma and the shape factors, basically based on the different person who started on this relationship. So we have here figures for the variation of N gamma with soil friction and the variation of the undrained shear strength is a view with depth obtained from field vein shear test. So we have here the shape factors that was evaluated by Michalowski based on elastoplastic model of soil and finite element analysis. So we have effect of soil compressibility. So for the effect of soil compressibility, you make use of the formula that was introduced by Meyerhoff, and there is modification because there is an introduction and additional, which is the soil compressibility factors. So to get the soil compressibility factors, you just have to follow this procedure so that you can get those soil compressibility factors. And you can make use of these figures for the variation of the soil compressibility factors. So we have here a sample problem for a shallow foundation wherein width is 0.6 meters, the length is 1.2 meters, and the depth of embedment or d sub f is 0.6 meters. The known soil characteristics are as follows. So we have here our characteristic of the soil given with the angle of friction, cohesion, unit weight, modulus of elasticity, and Poisson's ratio. We're going to solve for ultimate bearing capacity. Of course, for this one, you're going to follow the procedure to obtain the soil compressibility factors. Following that procedure, substitute the parameters, the variables given data. So you obtain this equation for your soil compressibility factor. And of course, you have to get, based on the angle of friction, which is 25 degrees, you can get from the table that N sub Q is equal to 10.66. And afterwards, once you have obtained your compressibility factors, your bearing capacity factors, shape factors, depth factors, and inclination factors, we're going to substitute that one to our equation for the ultimate bearing capacity, and we obtain which is 459 kilonewton per meter squared. Now we move on to our next topic, which is eccentrically loaded foundation. When to say that it is eccentrically loaded foundation? Eccentrically loaded foundation when the load acting on the foundation is not on the center of the foundation. It is away from the center of the foundation. So this is an illustration for an eccentrically loaded foundation. So for this one, of course, the nominal distribution, we know that our nominal distribution is given by this equation. You have maximum pressure is equal to Q all over BL, the load all over the width times the length plus 6m, the moment all over B squared all times L. And for the minimum pressure, you have Q all over L over BL minus 6m all over B squared L. So of course, you know that capital Q is the total vertical load, our M is our moment on the foundation. So based on the figure, shows that a force equivalent to that shown in the previous figure, we have figure 3.12a and 3.12b. You are given with this equation for the computation of eccentricity, which is E is equal to moment all over our applied load. So you can have this expression to get for the maximum pressure and the minimum pressure. Note that in this equation, this equation presented, the eccentricity E becomes B all over 6 and Q minimum is equal to 0. For E, which is greater than B all over 6, Q minimum will be negative, which means the tension will be developed. Because the soil cannot take any tension, there will be a separation between the foundation and the soil underlying it. So the nature of the pressure distribution on the soil will be as shown in our figure. So our maximum pressure would be equal to this equation. So we have a figure showing the nature of failure surfacing soil for a surface strip foundation subjected to an eccentric load. So the factor of safety is equal to the ultimate bearing capacity all over our applied load. So this is an illustration for the nature of failure soil in soil supporting strip foundation subjected to an eccentric loading. You have to take note, you have your d sub f equal to 0. The ultimate load is per unit length of the foundation. And then we move on to the ultimate bearing capacity under eccentric loading. This is based on the Mayer-Off theory. So this was proposed by Mayer-Off. This is a theory that being referred to as effective area method. So you have a procedure for determining the ultimate load that the soil can support and the factor of safety against bearing capacity failure. So if you're going to observe here, for step 1, you have to determine the effective dimension of the foundation. So effective dimension, we are referring to the effective width and effective length. So we want to use this equation that the effective width is equal to B minus 2E and L prime, which is the effective length, is equal to L. You're going to make use of this if the eccentricity is in the direction of the width of the foundation. However, if the eccentricity is in the direction of the length of the foundation, you're going to make use that L prime, which is the effective length, is equal to L minus 2E. And the value for B prime is equal to B. Then afterwards, step 2, you're going to have your compute for the ultimate bearing capacity. Then step 3, the total ultimate load that the foundation can sustain is given with this expression. So of course, you have now the presence of your effective area and effective width and effective length. Then step 4, you have to compute for the factor of safety, which is ultimate load all over your Q. And step 5, you're going to compute for or check the factor of safety against maximum pressure, or F is equal to ultimate bearing capacity all over the maximum pressure. Then you have here foundation with two-way eccentricity. Meaning to say, foundation with two-way eccentricity, the load is acting at a distance from the x-axis and at a certain distance from the y-axis. So this is the position of the load. It is acting away from the y-axis and it is acting away from the x-axis. So this is a two-way foundation. However, one-way, meaning to say the load can be acting at this point within the x-axis, so it is away from the y-axis, or the load will be acting on this point within the y-axis, so it is acting at a certain distance away from the x-axis. So that is one-way foundation. So for this one, if that is a two-way foundation, for the eccentricity, E sub B, that is along x, which is equal to m sub y all over the ultimate bearing capacity, or the ultimate load. Then E sub L is equal to m sub x all over the ultimate load. This is along x eccentrically foundation with respect to the x. This is with respect to the y. So for that, you can have the ultimate load is equal to Q prime times A prime. And your Q prime, the ultimate bearing capacity, is equal to this expression. And of course, your A prime is your effective area, which is B prime times L prime. And of course, for the effective area, there are 5 cases. So this is the first case. You have to take note of the position of the effective area for each cases, because there will be variations on the position of your B and the position of your L. So for this case, for case 1, you have E sub L all over L is greater than 1 all over 6, eccentrically loaded along Y direction is greater than 1 all over 6, and eccentrically loaded along X direction, E sub B all over B is greater than 1 over 6. So you're going to have this equation for case number 1. For case 2, you have this expression, E sub L over L is less than 0.5 and E sub B all over B is greater than 0 but less than 1 all over 6. So if that would be the case, the effective area is equal to this expression. Where in your B prime, you have this equation, and L prime, which is our effective length, you have this expression. For case 3, E sub L all over L is less than 1 all over 6, and E sub B all over B is greater than 0 but less than 0.5. So our effective area is given by this expression. You have to take note, this is the position for our effective area. In case 4, for case 4, it states that E sub L all over L is less than 1 over 6 and E sub B all over B is less than 1 all over 6. So for this one, you have your A prime, which is given by this equation. So our effective width is this equivalent expression. So you have to take note this. This is our position illustration for the effective area for case number 4. For case 5, this is being referred to as for circular foundation. So for circular foundation, in the case of a circular foundation under eccentric loading, as shown in our figure 3.19, the eccentricity is always one way. The effective area prime, A prime, the effective width B prime for a circular foundation are given in a non-dimensional form. Of course, for our eccentricity, it is one way because all throughout you have the same given for circular foundation. So you have here table 3.7, variation for A prime all over R prime and B prime all over R for a circular foundation. So we move on class to eccentrically loaded foundation according to Prakash and Saran's theory. So according to them, they analyzed the problem of ultimate bearing capacity of eccentrically and vertically loaded foundation by using the one-sided failure surface in soil, which is, this is the illustration for one-sided failure surface in soil. Then according to this theory, the ultimate load per unit length of the continuous foundation can be estimated using this expression. So this is the equation for the ultimate bearing capacity according to the theory of Prakash and Sarans, where you have N sub C, N sub Q, and N sub gamma. This is the bearing capacity factors and their eccentric loading. So if we're going to compute for the ultimate load, it can be given by this expression. And you have to take note that this one are the shape factors. And they recommended the value to compute for the shape factors using this equation. And they have here variation for your N sub Q for eccentric loading. So we have a sample problem. A continuous foundation is shown in the figure. If the load eccentricity is 0.5 feet, determine the ultimate load. Q's ultimate load per unit length of the foundation. You're going to use Mayer of effective area method. So using the Mayer of effective area method, you have this expression, and you can compute for the effective surcharge, which is 440 pounds per cubic feet. And this was the figure illustrated in our given problem. So for angle of friction, which is 35 degrees, from the table, you can have the value for N sub Q and N sub gamma. And to compute for, you can have your effective width, which is equal to 6 minus 2 times 0.5, which is equal to 5 feet. Because the foundation in question is a strip foundation, therefore B prime all over L prime is 0. So you can have this value for your capacity equation factors. So for this one, for the ultimate bearing capacity, you simply have to substitute to the equation and you obtain 30,351 pounds per square feet. And you have now the ultimate load, which is equal to B prime considering 1 unit length times